But at the equator, there's a really big temperature variation between what you see at the hot poles and the cold poles, with temperatures changing almost 130 Kelvin between the two at a given latitude. And even at the mid-latitude regions, around 45 degrees north or 45 degrees south, there's still about 100 Kelvin difference between hot poles and cold poles. And so there were some early predictions by Noble and Peters that these variations in the temperature environment, and particularly in these hot regions, you might get an interesting signature in the optical properties of Mercury's surface. Specifically, this process of Ostwald ripening, where you can grow nanophase metal particles to larger microphase particles that act as really efficient absorbers, and those can influence the optical surface. One effect would be darkening the normal albedo of the surface. And so this plot here is from some early experimental laboratory work from Gleiter, where they were measuring the diameter of iron particles with respect to the temperature that they were heating them at. And you're seeing the temperature of the experiments along the x-axis and the grain diameters of the iron particles on the y-axis. And what they showed is that at temperatures below around 200 Celsius, there's not a very efficient growth process that's occurring. But once you reach some sort of threshold temperature, maybe around 400 degrees Celsius, you get this very efficient growth process where the iron particles can thermally anneal and grow to larger particles in a matter of about 10 hours in the laboratory environment. And so Noble and Peters suggested that this process could be very efficient at Mercury, where you have high temperatures, but it wouldn't be so efficient on other airless bodies like the Moon, where you wouldn't have high temperatures to create this process. And so later on, there were some subsequent observations that said, okay, maybe there are some signatures of this process occurring on Mercury. So for example, Worrell used Earth-based telescopic observations. And some of his data are replotted here, where he's looking at the 650 nanometer to 850 nanometer spectral slope along the y-axis with respect to latitude from 0 to the North Pole. And he suggested that perhaps this sort of decrease in spectral slope closest to the equator might be relevant to this process of Ostwald ripening. And then later with messenger data, Nish et al. Created this Mercury Maturity Index, which is a parameter to describe the optical maturity of the surface. And Wilson et al. Noticed that there were some longitudinal variations in the maturity index on the surface, specifically that the longitude around 90 degrees, one of Mercury's cold poles, seems to have a relatively lower maturity index, so more immature compared to other longitudes. And then most recently, David Trang led a study using messenger VIIRS data to model microphase and nanophase iron and carbon across the planet. And what they found is that there was an enhancement of the microphase iron at equatorial latitudes with respect to cooler polar latitudes. And similarly, enhancement in the microphase iron at hot pole longitudes with respect to cooler cold pole longitudes. And they argued that perhaps this is some signature of Ostwald ripening affecting the optical properties of the surface. And so what we're interested in is whether variations in surface temperature also might correlate with variations in the normal albedo of the surface as measured by the messenger laser altimeter. So MLA is a really cool instrument to be able to look at the albedo because it carries its own light source and it's effectively measuring the surface at zero phase angle geometries. And so I can't emphasize enough all of the work that Greg has done to recalibrate this data. As you know, we saw a lot of reflectance data yesterday looking at the polar deposits, and that MLA data are archived and they're available in the PDS. But for this study particular, we are interested in the mid-latitudes and the lower latitudes where the bigger temperature variations exist in the longitudinal regions. And so this requires a different type of calibration. And I wanted to include this plot to give you an example of the challenging nature of some of the MLA data at lower latitudes. So what you're seeing are these colored pixels that represent the surface reflectance as a function of the range they were acquired at and the emission angle. And as you can see, at certain high ranges or high emission angles, the data are really quite unreliable. And so Greg has gone through the mission sort of piece by piece, timestamp by timestamp, to create more self-consistent maps that will allow us to conduct this type of analysis. So this is the map that we're now working with in the analysis, where we have looking strictly at the northern hemisphere, so 90 degrees down to the equator. And you can notice that there's the holes in the data, but we're working with the best we can, and we've binned the data into 1 degree by 1 degree latitude and longitudinal bins to help average out some of the reflectance variations that are inherent to the geology. And what we're doing is analyzing the surface reflectance specifically along the hot poles and the cold poles, which we're defining as plus or minus 20 degrees on either side. And maybe you've already noticed this right away, but of course there are various factors that can influence the albedo. It's not just space weathering. Some of the starkest differences relate to the smooth plains. So what we've done so far is separate the smooth plains as mapped by Brett's work, and then surfaces that are outside of the smooth plains. You can see this as well quantitatively, that the smooth plains are relatively brighter. This is consistent with various previous work looking at Mariner 10 data, suggesting that smooth plains have lower abundance of opaques and also relatively higher albedo. So as I mentioned before, we're a little bit sparse in the data as we approach the equator due to the orbit of Messenger. And this is showing you the counts of MLA pulses that we're using to create this map and to conduct this analysis. So it's very dense around the high latitudes, but it gets quite low around the equator. And to give you an example of that quantitatively, we have the number of pulses used for this analysis plotted on an x-axis that's on the log scale as a function of latitude. And so our MLA statistics stem from tens to hundreds of thousands of individual pulses the closer you are to the pole. But down towards the equator, sometimes we're relying on only tens to hundreds of pulses in a specific bin. So this is something that certainly we're looking forward to Bella helping improve the coverage and improve the statistics for. So to get into some of our results, what you see here are the plots where we have the surface reflectance on the x-axis with respect to the latitude on the y. And again, I'm separating the smooth plains versus surfaces that are not on the smooth plains. So the mean reflectance at 1 degree bins for hot poles are in red, for cold poles they're in blue, and then averaged across all longitudes for any bin are in black. And there are a couple of first order observations you can make. So starting with the polar latitudes, we heard about this yesterday, but definitely the presence of surface volatiles influences the albedo that we've measured. So for example, around 70 degrees north, we see that the reflectance across all longitudes begins to shift lower to darker albedos. This is due to the presence of those dark volatiles found in the cold traps. And then once you reach about 85 degrees north, where now water ice is stable on the surface, you have a shift back to higher albedo. This is attributed to the presence of surface water ice exposed directly at the surface. So this is consistent with previous work that we've published. But again, we're really interested in sort of this mid-low latitude region. So far, it looks like there are certain regions where maybe hot pole longitudes have relatively lower reflectance than the cold pole longitudes. But it gets a little bit more complicated. You can also begin to separate the two cold poles and the two hot poles. So one thing that we're seeing is that the 90 degree cold pole tends to have the highest reflectance of any of the 4 longitudinal poles. This is consistent with some of the earlier work that I showed, where Nish et al. Found a lower maturity index along this bin. Also, David Trang's work showed that the lowest amount of nanophase particles are predicted for this cold pole as well. But maybe you're also seeing we have results from the 270 degree cold pole, which are interesting as well because they appear to often be the darkest of any of the thermal longitudes. So right now we're looking at some more detailed studies of what can be influencing this cold pole. And it seems that the other three thermal poles might be oversampling bright cratering materials with respect to this pole. So a next step in this analysis is accounting for cratering materials as well, in addition to just on and off the smooth plains. So we're also looking at comparing the MLA results with MDIS. This is the low incidence angle map that the MDIS team put together from the MESSENGER mission. It helps to minimize shadows and really bring out some of the albedo variations of the surface. And so we're comparing it to the MLA map. We've resampled it to the same 1 degree by 1 degree bin. We've masked it to only be the areas where we have the MLA data. And what you see now on the screen is a comparison of the 4 longitudes with MLA on the left and MDIS on the right. You can see that generally the patterns are consistent. There are some areas that vary, but this is to be expected. MDIS uses a different calibration and has different viewing geometry to consider as well. But overall, I think this is consistent generally with what we're finding. And we can start to quantify some of that relationship too. We're looking at that now. This is a plot showing the MDIS reflectance on the Y in comparison to the MLA reflectance on the X. So to get into some discussion on why these variations might be occurring, I showed this plot before, but it's possible that at some of these hot regions in the lower to mid-latitude regions, where high temperatures could be promoting the growth of particles, that could be influencing the optical properties of the surface, potentially darkening certain areas. But of course, other processes can affect the surface properties as well, and especially when considering space weathering. So, for example, micrometeorite fluxes. So these plots were constructed by Peter Picorni. They are using his models that he published in 2018 for Mercury. But what he's done for these plots is look at the micrometeorite bombardment that you would get over the planet over a single orbit. And what he's predicting is that for one orbit you would start to get some sort of hemispherical difference where you'd have enhanced bombardment, which could create some sort of spatial variation in space weathering. But that's a very, very short time scale. So as soon as you consider 2 orbits of the planet, then you have sort of this symmetry. And then once the planet progresses over a single precession cycle, you would expect any sort of longitudinal effects to kind of average out. It does suggest that perhaps there would be some latitudinal effects that you would expect related to the albedo, and this is also a future step for the work that we're looking at now. Similarly, solar wind bombardment can influence the optical properties of the surface, but much like micrometeorite bombardment, these are expected to sort of average out longitudinal effects over long time scales. But they could also have an effect on the latitudinal distribution of space weathering effects. This is some plots from some old work, but the posters were just taken down, but hopefully everyone got to see size work as well, which predicted perhaps there's some sort of mid-latitude enhancement of bombardment on the planet. So overall, these sort of plots suggest that perhaps longitudinal variations would not be consistent with micrometeorite bombardment or solar wind flux. So it seems that really a thermal stress would be most consistent if there are variations. I will say that also latitudinal variations have been observed on the moon. So this is a plot from a study by Hemingway where they looked specifically at the 1064 nanometer surface reflectance of lunar Maria. And they saw this sort of symmetry across the planet where the symmetry was attributed to variations in the solar wind flux decreasing towards the poles. So with Bepi-Colombo, once we begin to have more data southward of the equator, perhaps we could be looking for hemispherical symmetries or asymmetries related to variations in space weathering. Okay, so to conclude, it seems that perhaps there are some low reflectance values at the low to mid latitudes in the northern hemisphere along the hot pole longitudes that could be consistent with this process of Ostwald ripening that Noble and Peters predicted to occur on the surface. In addition to the various avenues of research that I pointed out we'll be looking at, Dave Page is also working on creating some thermal models for the North Pole at the same resolution of the MLA data to help to quantify this exact relationship that we might be seeing. In addition, there's some future work going on. David Trang has a grant to be looking at the process of Ostwald ripening in the lab for Mercurian samples under mercury-relevant conditions. So we're very much looking forward to understanding how and when this process could occur. And then, of course, continuing to get more data in these lower latitude regions where you have very distinct variations in the temperature is something that we really look forward to with Bepi Colombo. Thank you.
For questions? Yeah.
Thanks, Ariel. It's great to see all this data getting even like more processed and improving, and yeah, your lines all kind of look like they fall on top of each other to me right now. So I guess I'm more like, does the composition of Mercury matter? I mean, you know, since it is a relatively iron poorer surface than like the moon, or do you just need so little iron that like the composition of the surface isn't really a factor here?
Yeah, some of David's work looked at iron versus carbon, and specifically for Ostwald ripening, it was kind of interesting what they found, because you would expect some sort of trade-off, whereas you were getting more microphase iron, perhaps nanophase iron was getting less, because that was what was growing. And they actually didn't necessarily find that difference, but they saw a distinct difference in the carbon. And so there was a trade-off between microphase and nanophase carbon. So they suggested that perhaps actually carbon might be more effective in this thermal annealing process than iron. So I know that's going to be a big factor of investigation for his lab studies. Yes, of course, the composition, I think, matters for something like this, but yeah, and another interesting avenue could be looking at the compositional terrains as a function of temperature and albedo.
Yeah, it's really interesting. I mean, because the question is too, if you don't find evidence for this, like, why not? Right? It's the reverse question.
Right.
Right.
Other questions? If not, I'm going to ask you one. There is evidence from the exospheric observation that the cold poles are trapping more efficiently, perhaps volatiles. So my question is, in the way it seems that the cold longitudes are enriched in volatiles. Will it change something in your, I mean?
Cut me off if I misunderstood you, but so once you get closer to the poles, and about 80 degrees to 90 degrees.
No, I'm speaking of longitudes. I mean, there has been some mass observations showing that in the exosphere we see a correlation between the quantity of material in the exosphere and the cold longitudes. And so it suggests that the cold longitudes are, let's say, a reservoir of these materials, which released along the year of Mercury. So my question is that it seems that these regions are particularly enriched in volatiles. So my question is that will it impact the albedo or some signatures in?
No, that the volatiles trapped in the exosphere, would those influence the albedo?
Yeah.
I don't believe so.
No. Okay.
Yeah.
No, trap in the surface. I mean, yeah.
Oh.
Yeah. There. You're right. Sodium, but if sodium is trapped, I mean, I would expect many things. Yeah, yeah.
I'm not sure, to be honest.
Okay. Thank you. So the next talk will be by Nicolas Botz, and he will speak about simulating micrometeorite bombardment of Mercury analog samples.
So thank you very much. So as François said, I will talk about how we can simulate micrometeorite bombardment of Mercury analog samples in laboratory. So this work, I'm just starting to do it with my PI, Michelle Thompson, at Purdue University. And so, yeah, she started this work a few years ago, and yeah, we will continue together. So my presentation will be as following. I will start with a short introduction with about space weathering, even if we already talked about this in the previous talk. I will present the samples and the methods we are using for this work, and showing some results and recap in the conclusion and draw some perspectives. So what is space weathering? So it's space weathering refers to processes that occurs on the surface of airless bodies, and we can identify three main processes. So first, micrometeorite bombardment, that are basically dust particles that hit the surface at very high velocities. The solar wind irradiation. And the last one is the cosmic and solar ray irradiation. So today we will talk about the first one, micrometeorite bombardment. And so these processes are altering the spectral, microstructural and chemical characteristics of the surface of Earth's bodies. And these effects vary depending on mainly two things. The heliocentric distance. So, for example, you will not have the same effects for the moon or for example, Jupiter moons. And the second effect, so the second dependence is the initial planetary surface composition, as, for example, has been showed by Lance et al. 2017. So you can have, for example, brightening if your initial surface is dark enough. So yeah. So what do we know about space weathering? So, for example, on the moon and on S-type asteroids, the space weathering is pretty well known. So mainly thanks to the sample return of Apollo missions. So on the left figure, you can see two visible infrared spectra of lunar samples. The blue-violet one is a sample that has been taken in an ejecta of a crater, so it should be a fresher material. And the red spectrum is a spectrum of lunar soil, so should have been exposed longer to space weathering. And what we can see is that we have a darkening of the spectra. And we also have a reddening. I hope I will convince you that there is a reddening, meaning that the spectral slope is increasing between the fresher material to the older material. And we also see very well that the absorption bands are, the depth of the absorption bands are decreasing pretty dramatically. So these are the first effects of space weathering, which are the spectral effects. We can also look at the microstructural effects of the space weathering. So for that, we can look at transmission electron microscopy. And so we can see that we have this melt layer that is created on the top part of the crystalline phase of your mineral. Here, for example, it's an olivine. And also, we can observe some often a vapor layer on the top of this melt layer. And lastly, We can also observe the inclusion of iron-bearing nanophase particles in the melt layer. As we can see here, there are some small dots that are these nanoparticles. So this was for the moon or ice-top asteroids. So what about Mercury? So Mercury, as we all know, has a unique composition surface. As we can see on this enhanced color mosaic of the Daring crater, we can see these blue, dark blue patches that are low reflectance material. So we know that the surface of Mercury is iron poor and also carbon rich. And Mercury is also very close to the sun, which is very important, which implies that there is a more intense micrometeorite bombardment and also a more intense solar wind irradiation. By more intense, I mean a higher flux, but also higher velocities. So, as we don't really know very well the space weathering on Mercury, we have to further investigate the space weathering of Mercury through laboratory experiments. So for that, we are considering pressed powders pellets of phosphorite olivine, which is a mineral phase that is expected at the surface of Mercury. We are considering grain size between 45 and 125 microns, which are also the range of grain size expected on Mercury. We are considering 3 samples here with various iron content. So the first one is the San Carlos olivine with 9% of iron, which is higher than what is on the surface of Mercury, but this sample is used for reference with previous laboratory experiments. The second one is FT004, has 0.53 weight percent of iron, and the last one has even lower iron content, 0.05 weight percent. And to account of the carbon content, especially in the low reflectance material, we also mixed the samples with powder graphite at 5 weight percent. So, as I said, we simulate the micrometeorite bombardment. So how do we do that? We irradiate the samples with laser pulses at Northern Arizona University, and we did first 1 pulse and then 5 pulses under ultra-high vacuum. This is a picture of the setup used to irradiate the samples. About the methods, so we are going from the less destructive methods to the more destructive methods. So first, we started with visible infrared reflectance spectroscopy to look at the optical and spectral characteristics of the samples. Then we did scanning electron microscopy to look at the morphological characteristics of the samples, and we ended with the so we did some FIP sections, so which are electron thin, to look in transmission electron microscopy in these samples to look at the microstructural and chemical characteristics of the samples. So first, the spectroscopic analysis. So we have here 3 samples that I described before. With each time we have the unirradiated spectrum in blue, the 1 raster laser in spectrum in green, and the 5 pulses laser sample in red. So we can see that the behaviors of the samples are different according to the iron content. For example, with the San Carlos olivine, we have a darkening, ultimately a darkening. of the sample. We have little reddening, and we have also decreasing of the 1 micron spectral absorption band depth. Whereas for the two lower iron samples, we have a brightening, and we have also a reddening and a decreasing of the absorption band's depth, especially for the lowest iron content sample. So now if we look at the morphological analysis with the scanning electron microscopy, we can identify two main textures, which are on the left a carbon-rich fluffy deposit, and on the right we can see a melt containing vesicles, these small holes in the melt. So these are the two main textures in the irradiated samples. And now if we analyze more specifically these thin FIP sections of the samples, if we start with the Sankaras olivine, we can look, for example, at the carbon texture, and we can see that they look like a global deposit, as we can see, and they are carbon-rich, as we can see on the right with this carbon map. And these globals are distinct from the graphite layers that we included in the samples. So these globals have been produced during the irradiation of the samples. And we can do the same thing for the FT004 sample. And if we look at, again, a tranche of the sample, we can identify this melt layer that I presented for the moon sample. This melt layer is enriched in silicon, is poor in magnesium and oxygen. So yeah, and it is uniform and basically amorphous material. Amorphous material. And finally, so these images have been taken just before I left Purdue University. This is my first image, so yeah, it is not very well resolved, I would say. For example, we should see this melt layer on the bright field image, but we are not, so sorry. But we can see that this melt layer is indeed, as the previous sample, enriched in silicon, but it is also enriched in oxygen and completely depleted in magnesium. So yeah. So to conclude, we have seen that the effect of space weathering are indeed dependent on the composition. Or here we have seen that the iron content are have an effect on the space weathering effects. We retrieved familiar results which have been obtained with previous studies which didn't include graphite in the samples. For example, the spectral reddening or the inclusion of nanoparticles. But we also observed new features like the carbon-rich fluffy textures. And so we will continue to analyze the samples, but we will also look at other samples that have been irradiated by hydrogen and helium ions to simulate the solar wind irradiation. And we will also consider other sample compositions, for example, including sulfur, to look at the effect of the volatiles in the space weathering processes. Yeah. Thank you for your attention.
Time for question? Yeah, okay.
I'm sorry, I missed which is the velocity or distribution of velocity that you are assuming?
The velocities of the micrometeorite bombardment.
Yes.
I think I'm not sure it's for the micrometeorite bombardment, but I have in mind that it's between 20 and 40 kilometers per second, I think, something like that.
Ah,
So it's pretty fast, faster than on the moon.
I would like to know, the experiment is performed at ambient temperature, correct?
It is at ambient temperature. Yeah.
Can you elaborate about possible variation at higher temperature representative of the Mercury surface?
So I also did some measurements with higher temperatures, but just reflectance for reflectance spectra. We saw that, for example, some samples have also a darkening, and also a reddening. However, I'm not sure if, in terms of which is the most dominant. I would say, how can I say that? Which effect between heating or irradiations is the most important, which the most dominant for modifying the spectral characteristic. But there are also some effects for the heating, and also I guess for the cooling, for the cold poles or the polar deposits.
And then I have another suggestion. I've seen in the photo of your setup, you have also a UV spectrometer, but today you are only showing spectra above 750 nanometers.
Okay.
So since there are many nanophase particles, I suggest you to look carefully at shorter wavelengths, where
UV.
possibly there will be Rayleigh scattering coming from the nanophase particles, which would be very, very diagnostic also to infer from a spectroscopic point of view the presence of these small grains.
Indeed, thanks for the advice.
Any other questions? Yeah, Nancy.
So I guess following up on that, if this, carbon-related stuff that forms was the dominant one, would it maybe be so dominant that it would drown out seeing the Ostwald, effect that Ariel's looking for? Is that a viable potential explanation or not?
So you mean the carbon global deposits that I showed?
Whatever this third bullet is, the new features observed, carbon fluffy thingies, yeah, that stuff, yeah.
So what is the question about these globals? About this?
I guess if this is dominant, if this turned out to be dominant, would it be so much more dominant that the Ostwald ripening is like happening, but it's just so small compared to this effect that you don't see it, and that's like why Ariel's not really finding it.
I guess that these globals are decreasing the content in graphite, so that's why I think we can have a brightening in the samples, I guess. So, yeah, could be the explanation.
Any other questions? No. If not, we are going to move to the next talk, which is going to be given by Carl Schmidt. Is going to deal with impact events observed by messenger UVVS.
Okay, thanks. I'm going to be talking about kind of a search that we did for some of the more transient events that could occur in the exosphere, things that are different from the seasonal behavior that messengers saw, things like ion sputtering, meteor impacts that might have short-term variability in them. And the strategy behind our search was kind of motivated by the sodium distributions. There's a couple different things that can liberate sodium from the surface regolith into the exosphere. Micrometeorite vaporization and ion sputtering are energetic processes relative to photodesorption and just thermal evaporation. And this plot also demonstrates a lot of mystery. Our community does not have a good consensus for the exosphere of what these energies are. The numbers are kind of all over the place. But in any case, we can use the partitioning of things that are above this escape speed here at 4.25 kilometers per second to just look at the tail, and that helps isolate the more energetic processes like vaporization and sputtering. So you'll see more of those escaping into the tail than you would on the day side of Mercury. And then the data that we use to search through are these messenger observations called tail sweeps, where you're out here at apogee, and you're staring up north back at Mercury and just taking these sort of fan sweeps through the tail. And you get a cross-section that looks something like this, where you traverse Mercury's shadow, and that turns off the sunlight that is exciting the gas, so you don't see it there. Now, in order to understand the sodium tail, there's kind of a complicated geometry effect that we need to discuss first. And all of that is just due to the 1 over r squared effect. It changes the amount of sunlight as Mercury orbits, so that moves the incident flux up and down. And the eccentricity makes you Doppler shift left and right by about 10 kilometers per second. And that really changes the excitation rate for how bright the gas ends up being. If you take a constant atmospheric production rate at Mercury for sodium gas and look at how bright it is as the orbit evolves, you get really large-scale modulations, more than a factor of 10. So you need to correct for that effect when you're trying to interpret real changes in the atmosphere that are due to column density. And this was kind of the messenger result that surprised a lot of us that were working in this field. We expected a lot of variability in Mercury's atmosphere, short-term variability from things like sputtering, and we knew that it would be present most in the tail because those transients are higher energy events and they should escape. And this is a plot of the sodium tail data that Messenger took with these fan sweep observations. And if I just take one distance down tail and plot the brightness as a function of season, it's very, very repeatable. There's very little variability in the data set, and it's very much a seasonal effect. And there are some interesting dynamics here. The sloshing effects that I've heard we've been talking about a little bit, where these cold pole longitudes that are sort of traced by the white line across the planet sloshes over to the other hemisphere. You can see that effect on the tail data. And there's some feedback in the radiation pressure where at certain points in the orbit, when you start to Doppler shift away from Mercury, you encounter more and more sunlight, and there's a positive feedback that gives more and more radiation pressure, and that's why this point of the orbit lights up more brightly than this part of the orbit. But if we were going to survey this data set now for variability, there's very little, and what there is sort of appears down here where not much is escaping. And the escape that we get here is from minor sources, things that are not the bulk atmosphere, but transients that are starting to show that their relative contribution is high because the background is low from the bulk atmosphere escaping. So there was a lot less variability than we expected, and what little there is kind of congregated near aphelion, maybe a little bit near perihelion. And in terms of the bulk atmospheric properties that we're working with, if you had cold gas here at, say, 600 Kelvin, well, if you're out here at perihelion, none of that should escape. The radiation pressure is just too low to give it enough boost. And you get too much seasonal modulation in the atmosphere. If you change your velocity distribution functions into the exosphere and make them hotter, 1200 K matches the data pretty nicely. And we think that's the temperature of photodesorption. And if you get up to higher energy things, like we had thought micrometeorite impacts are somewhere maybe around there, or sputtering, they don't modulate enough with season to reproduce the seasonal escape rate that we see. So looking at that data near aphelion, where we saw some variability, we then looked for the kind of anomalous data points that didn't fit the seasonal predictions. And we isolated 3 different events in the tail where the tail sweeps are not just a little bit different, but very different from passages with similar viewing geometry. So a typical passage with standard viewing geometry averaged over a few orbits is shown here in gray, and these events are in red, and they are significant enhancements by a factor of a few in the brightness of the tail. It's cut off right here, but most of what I'm going to be talking about today appeared in Cassidy 2021. That's the paper to look for. So the tail sweep data is a time series fundamentally, and if I plot this as a time series, you can see the steady state atmosphere here compared to the enhanced atmosphere. In order to know how enhanced it is, you need to have some background model for what the normal escape rate is. And for that, we used Matt Berger's 2014 model. It's the same as he published for calcium, but we just put some inputs for sodium in there that matched it quite well. And that's the black line. You can see it reproduces the steady state atmosphere, but it cannot reproduce these bright enhancements that are in the tail. So there really is something going on there. Now, a steady state model won't reproduce transient effects in the atmosphere, so we can't just use that model here. And so we added my 2013 model to this steady state Berger model. We added those 2 together. You can play those games in an exosphere. All the particles are collisionless, and you can just add 2 models together. It works fine. The free parameters that we searched and tried to figure out the properties of these events are just latitude and longitude, the time of the event, and the temperature. Here's an example of one of those model runs. The data of a tail sweep at sodium wavelengths is seen here in orange. The steady state model here is the dotted line. And added to that is this event up here on top, and you can watch the atoms sort of propagate down tail. So the sun is to the left. This impact was near the subsolar point, we think. And it was an impact. We weren't able to simulate these things with sputtered events of any significant duration. Once you get longer than even a few minutes, it really ceases to match the data. And we doubt that things like coronal mass ejections and significant sputtering events would be that short. So they sort of have to be impacts to do this. You can see the geometry of the planet is changing. That's because the Messenger spacecraft is moving as it's taking this data. And there's a little sort of scrolling white aperture there that slides back and forth. It shows up better in the next plot. That's the actual slit spectrograph that Messenger is using. So the geometry here is really messy, right? And you need a model like this in order to interpret the data. We had hoped that we could constrain things like the bouncing of particles around the surface. The exospheric particles could impact the surface and then bounce off. Do they accommodate to the local surface temperature? Maybe, maybe not. We had hopes that we could sort of work out some of those parameters, but it turns out this data in the tail is really insensitive to all that. Maybe on the day side it would be different, but we don't have that information. This is another event. It occurred pretty close to the dawn sector, so we're looking up from the south, and that's Mercury's dawn. And in terms of the total amount that is coming off in these impacts, it's not much. This is 1/2 kilogram of sodium is all it takes to see one of these enhancements. And 1/2 kilogram of sodium extrapolating the equations of Centala works out to be centimeter size impacts. I know that publication is a little bit outdated, but it's in that ballpark. These are not extreme events. They're pretty small impactors. And we've seen 3 in the tail sweep data. If you try and figure out statistically how many impacts like this there are at Mercury, it's about 1 a day. So Bepi Colombo will certainly be seeing these. And the most interesting one was this event in which we have not just sodium data, but data of sodium, magnesium, and potassium. Those are the 3 major species that the ultraviolet spectrograph on Messenger measured. And we see a strong enhancement in sodium and in magnesium, and calcium is noticeably absent. And that really stumped us at first because the explanation that was sort of the working theory for calcium was that it was generated by micrometeorite impact vapor. Now if I model this event, it seems like position-wise it occurred very close to the anti-solar point, and that's right where this measurement was sensitive because we're just above the night side. We're sort of scrolling back and forth with the spectrograph slit, and now we're starting to come closer up to the planet. And we've got sodium on the left and magnesium here on the right. And you notice the distribution of how this plume sort of spreads around Mercury is quite different between sodium and magnesium. The sodium sort of gets pushed down tail by radiation pressure pretty quickly, whereas magnesium, you start to see this column of kind of a spike-like feature evolve on the day side. And if you think about particle dynamics, if you launch a plume of particles in one hemisphere, the ones that don't hit the surface or escape are all going to try and go into orbit around the planet. And so that point there is where all of those orbits are crossing one another, and you get an enhancement in column density locally there. It doesn't show up in sodium because radiation pressure perturbs all of those orbits. We have some constraints on the temperature of micrometeorite or meteorite impact vapor through this modeling. We tested out a few different temperatures and figured out the chi-squared fit. And it's not really sensitive, but we can certainly say that it's much hotter than what everyone thought it was before. Sort of a few thousand Kelvin was the working theory for what we thought the gas temperature from an impact would be. And the best fits that I'm getting to these data for sodium, for all three events, it needs to be 10,000-ish degrees Kelvin, much hotter. And magnesium, I only have one event, so I can't say much, but the best fit was 20,000 degrees Kelvin. And we know from experiments by Berezhnoy and others that the temperature of different condensates in a fireball where the meteor hits is different. So it's expected that different species will be at different temperatures here, and that's what we're seeing. So thinking about those temperatures here, here's just a zoom in on that one event. You can see the tail is noticeably wider from the plume in magnesium. We can compare that to scale heights that MESSENGER took in the dayside atmosphere and think about how substantial a source micrometeorite impact vaporization actually is. And it's kind of tricky to do for magnesium. This is a paper by Amy Merkel showing that the scale height for magnesium kind of changes. It's different depending on when you look and where you look at Mercury. And sometimes it's as low as 3,000 Kelvin, sometimes it's as high as 10,000 Kelvin. They haven't seen it as hot as 20,000 Kelvin yet, but things start to get pretty degenerate once you're so hot above sort of 10,000 Kelvin that maybe it's workable. So it's hotter than we expected, and I'm not sure that we can claim that micrometeorites are driving the magnesium exosphere the way we've thought. For sodium, the story is a little bit more clear, and it's also interesting. You've got this cold sort of 1200 Kelvin component. That's this steep scale height here, and superimposed on that is another component. Tim Cassidy put that at 20,000 Kelvin here, but again, the slope doesn't actually change much between 10,000 and 20,000. So I would say that this secondary minor component to the exosphere is probably micrometeorite impacts, not sputtering. So we have some ideas through this kind of work of what the overall contribution of this source is. Thanks. Now in terms of where that event where we have multiple species in the exosphere hit, it was right around here near the high magnesium terrain. And it was probably close to the equator, but we are not that sensitive to latitude because we're at the south looking up. We're looking through latitude. So we have an abundance ratio in the plume of about 3 from my modeling. And the surface abundance of magnesium to sodium there from the MESSENGER X-ray spectra works out to be closer to 5. Those two are not too different, and if you think about the things that might push it one way or another, well, if the latitude were slightly different and I got that wrong in my model, that would lower magnesium. If the cold pole longitudes that we've been talking about in sodium were actually enhanced in the surface density, that would increase sodium. And so it pushes the ratio closer to what the exosphere ratio is. And now we get to the point in the talk where I tell you that everything that I said previously is slightly wrong. And I say that because concurrently we have these ground-based campaigns that are observing Mercury, and one of the things that we've been doing is looking at line widths in these emissions. And we discovered pretty quickly on that the line width changes as you go downtail away from the sun. So here's a measurement just behind the terminator, behind the day side, where the temperature that we get matches the scale height and what we expect, somewhere around 1100 Kelvin, 1200 Kelvin for sodium. It's colder for potassium here. That line width in potassium and sodium nicely matched the laboratory measurements by Yakshinsky and Mady for photodesorption or electron-stimulated desorption. They call it DIET, desorption induced by electron transfer. They're the same process. If I go downtail, a little bit farther downtail, not much, only 1 or 2 planetary radii, that gas is hotter measurably in that line width by more than 1,000 Kelvin. No one expected that. The geometry can't explain it. It's a 90-degree phase angle, and so why is the line width hotter? The picture that is our working theory is that this is the recoil velocity from photon resonance scattering. So if you think about the momentum that a photon scattering imparts, the incident direction here is always anti-sunward, so that cosine is 0 if you're thinking about the direction away from the sun. But then it scatters in a random direction, and when it emits the photon, there's some recoil momentum also imparted there. And on average, that is isotropic, so the direction cancels out. And all of us exosphere modelers have neglected it because it cancels out. But it's still an instantaneous momentum that's sort of a random walk, which is effectively heating the gas. And I think that's something that all of us have been omitting in our exosphere codes. I think it has strong implications for the lunar exosphere. And it shows up most in the species where there's a lot of resonance scattering, sodium, potassium, hydrogen. There's a lot of conclusions here. I think I'm starting to get pretty tight on time. And maybe I should stop there. And thank you.
Time for questions? Anna.
I want to ask something that probably is in the conclusion. Do you consider that magnesium is also probably released as magnesium oxide, and so there is also this to be considered when comparing to sodium?
We don't. So the working theory is that the reason we don't see calcium, and that is one of the conclusions, is that the impact was right on the center of the night side at the anti-solar point, midnight equator. And if calcium condensed as oxides, how are you going to break apart that molecule? It's going to break apart by photodissociation, but there's no sunlight, so it just sticks there and the cloud collapses. And that's the working theory for why we don't see calcium. Now we do see magnesium, and so the question is, maybe that molecule condenses, but if it condensed, it has to sort of condense in a collisional environment, and it has some temperature coming out. It's still mostly in atomic form right at the surface.
But to see the magnesium or calcium in detail, this also require radiation pressure effect. So probably calcium has not so much effect.
Calcium radiation pressure is higher than magnesium, but I think again the reason that we didn't see it amounts to photochemistry. That there was just no sunlight to break apart the molecule into an atom, and then no atoms to look at.
Very beautiful talk, compliments. I have a very naive question, and pardon me if it's too simple, but your assessment that calcium is not coming out is based on one event.
True.
Of 1 centimeter particle coming down. How can you exclude that is in chemical composition of the target simply? You hit a place that there were no calcium.
I don't know what the relative abundance of calcium is and how well constrained that is, but I think it would have to be pretty extreme to explain no signal at all. So I don't think that it's just and you're saying the size of the impactor. I mean, it's a few kilograms of gas. So yeah, it could just hit an extremely calcium rarefied region of the surface. That's an option here, and we shouldn't dismiss it.
Any last? Yes.
Just one quick question. So I was wondering what are the free parameters in your model and how you constrain them in some way. So especially on the position of the impactor or the direction, velocity, mass. I don't know.
The only free parameters are location, latitude and longitude, temperature, and timing of when the event was. So between those, I just ran a whole slew of a few hundred simulations and sorted by cross correlation and chi-squared and the usual sort of tricks to see what matched the data the best.
No questions, so thank you again. And we are now going to listen Martina Moroni, who is going to speak about micrometeorite impact vaporizations as a source for CAs and CAO exosphere along Mercury orbits.
So, good afternoon to everyone. My name is Martina. I'm a PhD student from Rome. And today I want to present my work about the calcium exosphere of Mercury that was generated by the micrometeorite impact process. First of all, I wanted to give an overview of the scientific context. We know that for analyzed body as Mercury, the material impacted directly the surface of the planet and released some particles that contributed to shape the thin exosphere. And this is the case of Mercury. And from the first time that was observed, the calcium is from the ground. And with MESSENGER mission, the spacecraft observed a persistent and high energy search of calcium that was enhanced in the dawn equatorial region of Mercury. What can I show in this slide is the plot that was the result of Burger works that show the total calcium in terms of atoms as a function of the different heliocentric distance of the planet from the sun. The works of Burger, the conclusion of their works is that this profile is consistent with a search with the high energy, about 50,000 Kelvin, and that was enhanced in the Dawn equatorial region. But the conclusion explained that there is a real, so they don't explain what is the search, what is the process that generates this height search. So for this reason, we can see that there are some open questions. The first is that why there is this dome-dusk asymmetry that we can see, that we can observe then in the calcium exosphere, and also which is the process that generated this energetic calcium. So if we talk about the different element of the exosphere, we can be the difference between the light element and the refractories. That is the case of the calcium. For the refractory are elements that are stronger bound with the surface of the planet, and for this reason the adjective of this element in the exosphere was justified from some energetic process. For this reason, we concentrate attention of these two processes, that was the micrometeorite impact vaporization and the sputtering. Now, if we talk about the sputtering, it could explain the high energy calcium that we see in the exosphere, but this process is not able to explain the dome-dusk asymmetry of the exosphere, because the energetic particles don't confine only in the downside, as it is seen in the observation. So for this reason, we can don't consider it the sputtering, and we concentrate only with this the first process, that it was the micrometeorite impact vaporization. So now we concentrate about which process generated this exosphere. I list two different processes. The first is the shock-induced dissociative ionization that was represented in this schematic figure, in which that is this one, in which the micrometeorite impact bombardment the surface and release the calcium in molecular form, principal as calcium oxide. But the neutralization of this molecular is so fast that, for example, and also for the simulation, we simulate that the micrometeorite impact release directly and only energetic calcium. It is interesting to some experiment in the laboratory that the impact of the meteorite. So the interest is that about the temperature of this vapor cloud that was generated from then the impact. Because we can see that the temperature is greater than 20,000 Kelvin. That was in accordance with the observation. The second process that I represent in this schematic plot is the impact vaporization and then the calcium oxide photodissociation. So also in this case, the bombardment of micrometeorite release in the exosphere calcium in molecular form. For this study, we consider only the calcium oxide. And in the second step, with the solar photon, there is the photodissociation that releases in the exosphere calcium and thermal oxygen. So this is in accordance with the observation, because we can see that justify very well that the only way in which we can see this process is in the downside, okay? Because the molecular are dissociated by the sunlight. So for this study, we concentrated on these two different processes. We use to reproduce the process the model of Alessandro Mura that was presented in the presentation of this morning. So I don't concentrate about to describe the model, but only to talk about the assumption that we can choose for this model. First of all, we talk about the calcium abundance. We fix the calcium abundance on the planet surface that is equal to 3.5%. That was a value that we chose from the literature. But from this value, we can consider that there is only a fraction of this calcium that was in the exosphere and that was in gas phase. And this fraction is estimated to be the 5%. then, only this fraction, we can make the difference between the calcium that was present in the exosphere as in atomic form, and the calcium that was presented in exosphere as molecular form, as calcium oxide. And the two different contribution is in ratio between them in 1 to 3. So we consider all these things about the calcium abundance, and also we simulated the two different processes. The first is the energetic calcium that was generated from the dissociative ionization and neutralization of the calcium oxide. The process we said before that we considered that only the micrometeorite bombardment released directly in the calcium with at a high temperature, 17,000 Kelvin, and so we not consider the lifetime of calcium oxide. In the second process, we simulated the thermal calcium that was generated from the photodissociation of the releasing calcium molecular, and we consider the temperature that was 4,000 Kelvin for the calcium oxide. So I linked out the parameters that we use for the model, and also as input of the model we chose a map composition surface. We reconstruct this map composition surface considering this map, that are the map you can see before of Pokorny, that represent the impact vaporization flux. This map represents the 6 different true anomaly angles in which the impact of the micrometeorite is concentrated in downside, and in which there is a maximum in perihelium and a minimum in aphelium. So in Pokorny works, they consider all the contribution of the micrometeorite that impact the surface. But for our works, we consider only the part of these maps that was involved for the calcium. Okay, so now we show the result of the simulation. Okay, this represents the energetic calcium exosphere only at perihelium. We can see that the coordinate system was represented by the x-axis that was in red that point to the sun. So we have the sun to the right of the figure. The y-axis that represents the plane of orbit of the planet of Mercury, and the z-axis that was positive toward the north. The red figure represents the down hemisphere of the planet. While the right figure represents is a vision of the pole north of the planet. We can see that there is evident asymmetry of the calcium exosphere, in which the exosphere is denser only in the downside. So this kind of process confirms the observation of calcium exosphere of Mercury. We repeated the same simulation for four different true anomaly angles. We have the case of perihelium, the case of aphelium, and also other two angular, that was 90 and 2017. We can see in all the plot that there is an evident enhancement of the calcium exosphere in the downside, with a maximum in the perihelium and a minimum in aphelium. It is what we expect from the simulation. So now we compared the first process with the second, that was the thermal calcium exosphere, also in this case at aphelium, that was generated from the photodissociation of the calcium oxide. In the up of the slide, we can see these two figures that represent only the calcium oxide exosphere. That was generated directly from the impact of the micrometeorite on the surface. The first slide is the downside, the vision of the downside, and the right figure is the vision of the pole north of the planet. In this case, we can see that there is an enhancement. We confirm the enhancement of the calcium exosphere in the downside. The figure at the bottom are the figure of the calcium exosphere that was generated from the photodissociation of the calcium oxide. And in the same way, this one is the plot of the downside of the planet, and the right figure is the vision of the pole north of the planet. We can observe the different density of the two exospheres, in which the exosphere of calcium oxide is denser than the calcium, and also we can see the different spatial distribution of the figure. In which, for example, in the calcium exosphere, there was the concentration, the enhancement of this element only in this quadrant. This is the reason. The next, we can see better in this slide, in which I reproduce the same exosphere of thermal calcium in 4 different true anomaly angles. We confirm that for all the 4 plots, there is an enhancement in this quadrant of the figure. That is the reason is because this is a process that depends on the sunlight. So we have a peak, a denser zone, a denser area that was in the downside. We can also observe that there is a maximum in the perihelium, while there is a minimum of the density of the calcium exosphere in aphelium. But another thing that I want that you observe is the difference in the spatial distribution of the exosphere between the thermal calcium and that the exosphere before that was the energetic calcium. The thermal calcium was concentrated only more or less in this quadrant at the difference of the other energetic calcium exosphere that was concentrated in all the down hemisphere. I wanted to show this other picture that represent a 3D vision of the calcium exosphere, and in which the 3 figures represent the projection along the 3 different coordinates of the calcium exosphere. We in this plot, I consider the summarize of the 2 contributions, that was the thermal and the energetic calcium. So we confirm the enhancement in the downside, so the asymmetry on dusk is very clear in this vision, but only, I don't know if we can see, if we concentrate attention on this figure, we can see that there is also an asymmetry between this quadrant and this other quadrant. That was more denser than the other. This because in this quadrant there is the sum of the contribution of the thermal and the energetic calcium, and so there is a zone denser than the other. So in this slide I represent the density profile of calcium oxide and of the 2 different components of the calcium, thermal and energetic, as a function of the Mercury radius between 1 and 3. So we can see that the contribution of the calcium oxide exosphere is denser than the other, and the difference between the 2 components, the energetic and the thermal, and that for all the spatial, for all the radius, we have a denser calcium energetic exosphere in comparison with the thermal. The last result that I wanted to show is the comparison between the simulation result and the data from the messenger observation. This is the first. This is the same image that I show in the first slide. So it is the result of data burger, and in red there are the result of our simulation. So we can see that the simulation are consistent in this comparison with the data burger. We can observe that there is a difference between the 2 lines on a factor more or less 2. This difference could explain because we assume that the composition of the calcium on the surface planet is to be homogeneous. We chose the 3.5 of the surface, and we don't consider that there are some regions that are denser in the calcium surface. But these sure are future work. Another thing that I wanted to underline is the presence of this peak that is around the 13 degree. That was justified for the moment when one of the possible reasons is the contribution of some string comet, like for example the Henkel comet, that could contribute to show this peak in this angle. Also, this is not considered for the moment in this model, but will be a future work. So these are the conclusion. I only make a summary of what we do. So we study the calcium exosphere, and we show that it is not symmetrical, so it is an evident dome-dusk asymmetry, and in the exospheric calcium of planet. And we simulate the two different contributing of the thermal and the energetic calcium in the exosphere. And we underline that the contribution is more consistent from the energetic calcium. We compare all this with the observation, and we can see that it was more consistent. I said before that what are the future work. Sure, we wanted to consider not only the calcium bounded with the oxygen, but also the other kind of molecular. And first of all, they wanted to also to integrate with our model other contribution of this micrometeorite, for example, the contribution from the comet. As the last slide, I want to show this in very quickly way to see what can be an interesting orbit to observe or to give more information about this element, the presence of this element in the exosphere. So at the top there is a Strophio picture because we think that is very important the contribution of this instrument aboard of Baby Colombo to give information about not only the calcium element but only the molecular that are present in the exosphere. I only represent a possible orbit that was interesting, that is the orbit along the planet terminator, and I represent the Mercury in two different, in the spring and the autumn, because maybe could be the more interesting orbiter to study the dome side of the planet. As last, so I talk about Strophio, but there are also other instruments aboard of experiment aboard of Baby Colombo that could help to study the calcium element that are Phoebus and MDM. So thanks for attention.
We have time for one or two questions. Yep. Behind you, you have.
Well, question, comment. At the beginning, you justify your that you neglect sputtering because it's not down-dusk asymmetric.
Yeah.
That was.
Yeah.
Okay. It can be. I think it can be. So, plasma precipitation. In some models, you have down-dusk asymmetry. There is a paper on proton precipitation, which is very nice, last year or 2 years ago, Fatemi 2020.
Okay.
And he did like 10 cases, and you see they have down-dusk.
So that justify the enhancement, so the down-dusk asymmetry?
Yes.
Okay.
And maybe you can get a factor 2 if you do micrometeorites plus plasma precipitation. If it's of the same order, you get double ejection. Oh.
Thank you.
comments is I saw the presentation by the Phoebus team, and I saw that you found a kind of double component of calcium. So it could be interesting to see if the double component is consistent with this double population for thermal and energetic calcium. So could be nice to see.
Thank you. Any other comments or questions? If not, let's move to the last talk of this conference, and which will be given by Thomas Carlson, and it will be about messenger observations of short, large amplitude structures, SLAMs, in the Mercury foreshock.
Okay, thanks. This is some work I've been doing together with Ferdinand Plaschke, and I realize that there are quite a few people here who have not been exposed to plasma physics and magnetospheric physics, so I'm going to give you my 30-second plasma physics course. So a plasma is an ionized gas showing some collective behavior, meaning there's enough ionization that electromagnetic phenomena become important. And the ionisation can come about by heating, as in the solar wind, or, for example, by ultraviolet radiation in the Earth's ionosphere. And I guess Mercury would have a weak, what we could call a weak exo-ionosphere. Now, most of space plasmas are magnetized, meaning there's a strong enough magnetic field to dominate the particle dynamics. So a charged particle moving with a certain velocity will feel a force perpendicular to the velocity and the magnetic field. So it will begin to gyrate around the magnetic field. Along the magnetic field, there's no force, so the particle can move easily along the magnetic field. So plasmas are stuck on magnetic field lines. That's why we, for example, can see coronal loops, magnetic loops sticking out of the solar surface, or to see that the northern lights at Earth are organized along the geomagnetic field. Now, okay, SLAMs, short, large amplitude magnetic structures. For Mercury and Messenger, it's been quite fruitful to have a look at regions and phenomena at the Earth's magnetosphere and check if they exist also at Mercury, and if so, compare and contrast. So let's have a look at SLAMs at Earth. And first of all, let's have a look at the bow shock, where this takes place. So if you have a supersonic gas moving across an object, you will have a bow shock. So this is a wind tunnel experiment, where you can see the shape of the bow shock here. And this is a simulation, a glaciator simulation, where the solar wind, supersonic solar wind, encounters the Earth's magnetic field. And you can see the very similar shape of the bow shock. Now, of course, there's some extra complexity because we have a plasma. So we have all the electromagnetic phenomena as well. So, for example, you can see maybe these fluctuations here. These are ultra-low frequency ULF waves. And you see they occur in a region where you have an interplanetary magnetic field, the solar wind magnetic field in a certain configuration. Let me, okay, that's just a blow up. Let me say that in some more detail. So why this happens is that part of the solar wind, some part of the solar wind particles are reflected at the bow shock. Now, when you have the interplanetary magnetic field perpendicular to the normal of the bow shock, as we saw, the plasma particles are stuck on the magnetic field lines, so that the reflected particles can't move away very far from the bow shock. On the other hand, if the interplanetary magnetic field is almost parallel to the normal of the bow shock, they can begin to gyrate around the magnetic field and move quite far upstream of the bow shock. Now, plasma physically, this is a very unstable situation. Two counter-streaming beams that will generate these kinds of, for example, these kinds of ultra-low frequency waves. Now, for reasons we don't quite understand, these ultra-low frequency waves, which at Earth have a period of around 30 seconds, can go very non-linear. Some of them might stay in a linear stage where the delta B, the wave amplitude, is comparable or smaller to the background magnetic field, but they can also go non-linear. And when they go slightly non-linear, we typically call them shocklets. When they go very non-linear, delta B over B greater than 2, for example, we call them slams. So here's an example of one slams. It's one slams in the singular. Now, the role of these slams are manifold. They can be thought of as making up the whole quasi-parallel bow shock, which was suggested already by Steve Swartz in 1991. So you can think of the quasi-parallel bow shock as this kind of foam of bubbles, of slams, continuously being formed and coalescing into the quasi-parallel bow shock. And this has many, many consequences on, for example, the shocked plasma in the magnetosheath behind the bow shock. It can have consequences for acceleration processes at the bow shock. The bow shock is known to be able to accelerate particles to very high energies. And here you can see also this is a measurement from the upstream solar wind, where you have these ULF oscillations, which also creates a high energy background of ions. And you can see also the slams actually disturbs and disrupts the solar wind beam here even further. Okay, one final thing about slams at Earth. If we look at their polarization, it's typically an elliptical polarization in the plane of, medium, maximum, minimum variance analysis plane. Just means the planes where there's most of the magnetic field variation takes place. So, do we see this stuff at Mercury as well? Well, for a long time, we thought we didn't. We thought we saw these ultra-low frequency ULF waves, which, by the way, at Mercury have a period of around 1 to 3 seconds, rather than 30 seconds at Earth. There's also, that's the black lines here. There's also superposed some higher frequency waves here. And Sundberg looked at a small sample of this foreshock region, the region upstream of the quasi-parallel region, and said that, no, we don't typically see this. We might see these shocklets, which are mildly nonlinear here, delta B over B less than 2 typically. And myself made the same conclusion in another study based on the fact that if slams have a similar scale size at Mercury than at Earth, they would more correspond to a global reformation of the quasi-parallel bow shock. And you wouldn't see these leaking slams that you sometimes see at Earth, kind of detaching themselves and going back into the heated, shocked magnetosheath. But in the context of an ISI group, where Ferdinand and I were working together, we decided to go back and re-investigate the whole messenger data set. So we ran an automatic search looking for structures in the solar wind, the foreshock region upstream of the quasi-parallel bow shock, to check if we had small-scale variations with delta B over B greater than 2. And here's a very promising example. So you see in the ion data here, you see the shocked and heated magnetosheath plasma behind the bow shock. Here's the bow shock, here's the solar wind beam. And you can see this broadening of the solar wind beam typically associated with these foreshock regions upstream of the quasi-parallel region. And you see also some increased oscillations here. Those are the ULF waves. There are some further foreshock structures here, and there's a mode change in the instrument here, which makes it look a bit different here at later times. Now look here in this region here. This is the absolute value of B, or delta B over the background B here. And you can see in this region with a very low magnetic field, which I don't think is a coincidence, by the way. We'll come back to that. You see this very promising structure with a very high amplitude. You zoom in a little bit here. Okay, it's looking promising. You zoom in a bit more, and here they are. Really nice slams, short, large amplitude magnetic structures. You can see they are embedded maybe in a, it doesn't show very well here, but they're embedded in a general ULF wave field. Some of these periods go very nonlinear and create these structures. And all these three structures, they are also linearly polarized, very similar to what we see at Earth. So for the whole mission, we saw around a little bit more than 400 of these structures, which is not a great number, much less common than on Earth. But still, it's not zero. So here are a couple of other examples. I won't talk too much about them. I'm trying to create a little bit of a semi-manual classification, which I think can be useful if we want to compare to simulation results, but the most typical ones are seen in this general background of the ULF field. I'm going to skip this. But we can now have a look at some of the properties of these slams and compare them to the properties of the Earth slams. So for example, the scale size, the temporal scale size, are typically less than 1 second, which is a bit smaller than those at Earth, maybe not fantastically much. There's not really any good statistics on Earth. We have to work on that as well, but the ones we have seen at Earth are typically a few seconds. So this is maybe consistent with that the original ULF fields have a shorter period at Mercury than they do at Earth. They are quite wimpy. Delta B over B should be 2 for them to be called slams, and they're not that much more nonlinear than that. Okay, there's a tail, but still. Now, this I think is the most important slide. This I think is the explanation why we see them so rarely at Mercury compared to Earth. In order to get this nonlinear evolution, we should have a pretty strong shock, meaning there should be a pretty high Mach number. Now, in space, the Mach number is defined not by the sound speed, but by the Alfvén speed, the Alfvén velocity, which is the velocity of another information-carrying wave, the Alfvén wave. And that the velocity is given by the magnetic field strength divided by the square root of mu naught and the density, the mass density of the plasma. So you see that, okay, we can't really calculate rho from the ion measurements in the solar wind. But we know that on general, for smaller magnetic field in the solar wind, we should get a higher Mach number. So we can compare the magnetic field strength for all our slams compared to the general magnetic field strength distribution of the solar wind over the whole mission. So we see that we see the slams when we have a very weak solar wind magnetic field, meaning we have typically a much higher Mach number than statistically common. So I think, and well, we heard earlier today also that typically the Mach number at Mercury is much smaller than the Mach number, the Alfvén Mach number at the outer planets. But of course there will be times when the magnetic field is weak and we will have a quite high Mach number. So another way, so this is why I think this is no coincidence that you see these slams in this region of a low solar wind or interplanetary magnetic field. Now we can test this in another way. Okay, we don't have real density measurements, but we can use Enlil solar wind modeling, which is based on photospheric observations. And they are pretty good. This model is pretty good at providing background parameters, at least at Mercury orbit. So using those measurements of those that modeling of the density for our particular events, we can see that we can calculate the Mach number. And we see for the general solar wind, the Mach number is typically 5, maybe at Mercury. But we have this totally different distribution of Mach numbers for our SLAMS events. So they happen at high Mach numbers. High Mach numbers can drive nonlinear processes creating these SLAMS. And okay, I'm basically going to stop there. I'm going to show some other results at a later presentation. We can now go on to have a look at the detailed properties of these structures, but I think I'll just drive home the main point here. We do see SLAMs at Mercury, and they're less common than at Earth simply because the Mach number is typically much lower at Mercury, but sometimes the Mach number can be high enough. And they are smaller than on Earth, probably simply because the pre-existing ULF wave field has shorter wavelengths. And okay, you have to trust me on this, they seem to form very near to the bow shock, nearer than they would at Earth. And finally, of course, at Bepi Colombo, we hope to be able to study these at much greater detail. For example, we can have a look at the electric field and see if that is important for example, particle acceleration at the SLAMs and at the bow shock in general. So I'll stop there.
Is there any questions? She was first at once.
Thank you, Thomas, for the very nice and clear presentation. I have maybe a naive question. So you compared Earth and Mercury, which are magnetized planets.
Yep.
How about Venus and Mars?
This is a very good question. My plan is to have a look at all these other planets, and I made some very preliminary studies, and we can, I think, see them also at the non-magnetized planets, and they look very similar. They exist in this ULF wave field. They have similar amplitudes. They even have this signature that you sometimes see at SLAMs at Earth, these Whistler emissions at one side of the SLAMs. So you can see them also here at the Venus SLAMs, Earth SLAMs, Mars SLAMs, the Jupiter SLAMs, and maybe even at the Saturn SLAMs. So I think these are a very general and phenomenon.
Thank you.
Sorry, Anna, you had a question? Well, let's do this first.
Oh, okay. So I'm not a I don't know a lot about magnetospheres, but the combination of a low magnetic field strength and this really regular pulse sounds to me like it'd be really good for getting an induced response in the planet. Can you use these to probe the conductivity structure?
Maybe this is a contended subject. If these ULF waves really propagate through the magnetosheath first and then into the magnetosphere, maybe this is something we're studying at Earth. I'm working also with the Vlasiator people to combine simulations and cluster and MMS observations to check if they do. If they do, this would be one source for these ULF waves. Otherwise, there are other sources for ULF waves inside the magnetosphere which we can use. This could be one complementary mechanism.
So I see that the difference between different planets is also the time scale.
Yes, yes.
Is very
which is also, I think, related to the different time scales of these ULF waves created in the foreshock. Maybe. I mean, these are just a few events, but certainly it's striking the very different time scales.
We should try to see that this kind of slam only in the perpendicular direction, so close to the subsolar point of the Bow-Shock, because you need the perpendicular Bow-Shock.
The parallel. You need the quasi-parallel.
Quasi-parallel.
But at Mercury they will probably just be generated quite close to the Bow-Shock. At Earth, I think they will be further upstream, but this, I think, is a difference between Mercury and Earth.
Okay. Now, did you try to see if during the flyby the conditions are favorable for?
No, I haven't done that. I think. No, I've raised the question in some meeting if it was a quasi-parallel or quasi-perpendicular Bow-Shock, but I haven't got a clear response. Yeah.
Probably now we have some.
I was just wondering what you had in mind for in your last slide for PWI experiment. Which subset do you have in mind? Search coils, and you could add as well
anything.
Particle sensors.
Absolutely. Right? I mean, this is a plot from cluster, MMS at Earth, and particle measurements are certainly very interesting to study. For example, the energization and acceleration of ions at these things. So everything, we should look at all instruments, of course.
Okay.
I'm just mentioning the electric field because I'm part of the PWI team.
Okay. No other questions? Let's thank the speaker again. So it's time to close this conference. If you have any question concerning your travel back home, please let us know. We are still here for till the end of the afternoon if you have any problem. Also, if you want to organize a last-minute team meeting, you can use the room downstairs where there was the real-time retransmission. There will be actually here in this room an MPP team meeting starting in about 10 minutes. The only point is that you need to leave, not like yesterday at the museum. You need to leave before 6 because the security is leaving at 6. So if you plan to have a quick meeting, you can have, say, the next hour for dedicated to that. For the sure, Stefano.
For my American colleagues, I see a few of them right here. The ban for traveling into the US without a COVID test has been lifted as of Sunday. So, no testing if you're flying on Sunday.
Okay, so next step is, I guess,